So it is the second condition for the column. Column with second condition or case 2, where both ends are fixed. Both ends of the column are fixed. So let us consider a column. So initially which was straighter, and here both the ends are fixed. Both the ends are fixed. So let us consider these ends are fixed. That is end A and end B. Both the ends of the column are fixed. Okay. Now, when the column is applied with load at one of the end, so it is at end P, end B, a load P is applied. So this is the buckling load, which is applied at one of the ends. So when it is applied at the end of the column is going to deflect, or it is going to deform in this shape, right? So just like if you just hold some of the elements, so something like spring or something, if you just hold it and you just press it at one end, it is going to deflect in this manner. It is same as that, right? In this case one also it is same, only in that case it was hinged at one end. At here it is completely fixed at both the ends. Since it is fixed, there are reaction forces, that is a reaction moment that is going to induced at the fixed ends. So since it is going to deflect in this direction, the reaction force is that which is going to be formed in the opposite direction. So that is the moment it is going to be applied in the moment is produced in the opposite direction. So this is the reaction force. Since it is deflecting in this direction, the reaction moment will be in the opposite direction. Will be in the opposite direction. So this is the reaction moment, M. Okay. So now we are considered this initial beam. Initially, the beam AB. AB is the beam which is fixed at the end A and B. It is completely fixed and it is having the length L. L is the length of the beam. And P is the buckling load which is applied, or Euler load which is applied at one of the end. Due to this load, the beam is going to deflect in this direction. So the reaction moment is going to be induced in the opposite direction to the deflection. So that is the moment is taken in the opposite direction. That is the reaction moment. Okay. So now to derive the expression for Euler load, so let us consider a section. Let us consider a section just similar to last derivation. So we are consider a section XX, which is at a distance, from one of the end. That is, we are taken from the end B, which is at a distance small x from one of the ends. Okay. So now, let us consider the moment at this section, the bending moment at section XX. So it is given by similar to last, it is MXX. So moment at this section. So let me consider to one of the side. So moment at this section. So it is the force and this deflection, let this deflection be y, and let this deflection of the beam with respect to initial position, let it be small y, right? So now the moment is force into distance, the force is p, the distance is y at this point. At this point, the distance is y. So the moment will be, so what all the moment that is acting at this section you need to consider. So since it is going to be creating, the beam is bending in this manner as similar to last, right? It is giving concavity at this end with respect to initial straighter beam. So the moment is negative. With respect to sign convention, the moment is negative, minus P into Y, minus P into Y. And also there is a reaction moment that is M, that also you need to consider the total moment at this section. So this is the reaction moment, it is going in the opposite direction. It is going to bend this beam in this reverse manner. So it is positive. That is, it is going to create the sagging, it is positive, plus M, plus M. The total moment at this section XX, so moment due to the load and moment due to the reaction. So it is positive, whereas this, it is going to create the concavity at the inner end with respect to straighter beam, so it is minus P into Y. Okay. So in the last class, last derivation, we know this. M into XX moment at any cross section of the beam which is deflected, which is given by d square y by dx square, d square y by dx square into ei, ei into d square y by dx square, right? Is mx, that is equal to minus p into y plus m. Or you just rearrange this e into I d square y by dx square plus p into y is equal to m. Okay. So this you need to remember, as I told in the last class itself, this is the term which is the moment at any section due to the deflection which is happening on the beam. So just rearrange this, d square y by dx square is plus p into ei into y is equal to m by ei. Okay. So general equation for this differential equation, it is given by, it is of the form same as we told. It is, you need to remember the equation, general equation, the solution for the above equation, solution for above equation. So by, it is a general equation. So by the, for the differential equation, for this differential equation, it is given by, that is C1 cos x into root of p by ei plus C2 x into root of, sorry, C2 into sine x into root of e. This term is coming to other end, the constant. It will be E and E gets cancelled, plus M by P, plus M by P. So this is the solution for differential equation. That is y is equal to C1. We need to remember this. To call this as equation 1. Okay, next. You just differentiating, is dy by dx will be equal to differential of cos is minus sine minus C1 sin x Differential of this second term, differential of sine is cos x into root of p by ei into differential of this x into constant into root of p by ei. Differential of this constant is 0. So call this as equation 2. So now apply the boundary conditions. So applying the boundary conditions. So at the point A, so this is here, right? At the point A and B, right? At point A, x is equal to 0. Along this length, when you take x is equal to L at point B, okay, at the point A, there is no deflection. So when you move along the beam, the deflection is maximum at this point, so that is y. So as we move along the point B also, deflection y is 0 here. So apply that boundary condition when x is equal to 0 and x is equal to L for these two equations. For these two equations. So first apply boundary conditions. So that is at x is equal to 0 at this point, deflection y is equal to 0. And also there is no slope at this point. So if you take any slope for this curve, right? So that is dy by dx is the slope. So and also the slope is 0 at the point dy by dx is 0. At this point A, slope is also 0. So apply these two boundary conditions first. So at x is equal to 0 and y is equal to 0, add equation 1. So with respect to equation 1, x is equal to 0 and y is equal to 0. Just apply for this equation, you will get, so 0, y is 0. So x you put 0 in this, so cos 0 it is 1. So C1 plus C2, sin 0 it is 0, the constant will be remaining. So it will be 0 is equal to C1 plus 0 plus m by p. So C1 will be equal to minus m by p. So next, apply the boundary condition for equation 2. For equation 2, so that is dy by dx is equal to 0. For equation 2, dy by dx is equal to 0 and x is equal to 0. So with respect to equation 2, x is equal to 0 and dy by dx is equal to 0. So substitute, it is 0 is equal to C1 sine, so this term will be neglected. Okay, so here will be remaining with C2 cos 0. So it will be 0, that is equal to C2 into root P by EI. Okay. So here C2 root P by EI will be equal to 0, but P is what? P is the Euler load. P is Euler load or buckling load, right? So this cannot be 0. I want to find the equation for P. So P cannot be 0. Therefore, C2 will be equal to 0 and P is not equal to 0. Okay. Now you substitute all these values what you got in this equation 1. Therefore, you will get y is equal to C1 is what? Minus m by p minus m by p minus m by p into cos term, cos x root p by ei plus C2 term is 0, C2 is 0, C2 is 0, therefore it is remaining with plus m by p, plus m by p. So this is the above equation. By applying the constant C1, C2, y equation we got. Next, apply the second boundary condition at x is equal to L at this distance, at x is equal to L. So there is no deflection, y is 0. Next, this is the first boundary condition. Next, you apply the second boundary condition at x is equal to L. Deflection is 0. You can see there is no deflection at this point at all. So therefore, you apply this to the above equation. So we have got this y reduced equation. Therefore, y is equal to 0. You apply here. It will be 0 is equal to minus m by p cos x is equal to L. Cos L into root of p by ei plus m by p is equal to 0. So you just reduce this to take this to the other end. Therefore, m by p cos L root p by ei will be equal to m by p, right? Right. So m by p gets cancelled here. So here it will be remaining with 1. So cos L into root of p by ei will be equal to 1. So when cos theta will be equal to, so if you take this as a theta term, so when this value theta term will become, I want this to be how much? To cos theta will be 1. So it will be cos 0, right? Or cos 2 pi or cos 4 pi. I will get this value as 1. So therefore when, so since L into root of 2 root of p by ei term will be equal to 0, 2 pi, etc. 4 pi or etc. Any other value, any even values of pi. So I will get this cos value as 1. Okay. So since I want to find the load, Euler load, let me take the positive value, take positive value or non-zero value. Take a non-zero value or it is non-zero value. Since I want to find the expression for P, take a non-zero value. Therefore, L into root of P by EI will be equal to 2 pi. That is equal to 2 pi, or you just remove the square. I want expression for P, squaring on both ends. So L square into P by EI will be equal to 4 pi square, or P will be equal to 4 pi square EI divided by L square. Right? So this is the expression. Or you can rearrange and also you can write P can also be written as pi square EI. I'll take this 4 to the denominator. So it is L by 2 whole square. So this is the final expression what you can find it in books. This is the expression for Euler load. Expression for Euler load for a column which is fixed at both the ends, or it is Euler load, or we call it as buckling load, P. So you need to remember this equation. So let us call this as final equation 3, I think. So 3 is the equation for Euler load for a column which is fixed at both the ends. So still we have another two cases, that is it is fixed at one end and 3 at another end. And fixed at one end and hinged at another end. So any one derivation most probably you may have in the exams out of these four.